learned in school that particles are tiny objects, small pieces of matter moving through space like microscopic bullets. Predictable, definite. If you know where they are and how fast they're moving, you should be able to calculate where they'll go next. For centuries, physics was built on that exact assumption. The universe behaved like a machine. Every cause produced a clear effect. Every object followed a path. Reality made sense because it stayed consistent, whether anyone looked at it or not. Then, an experiment shattered that certainty completely. Imagine a wall with two narrow openings cut into it. Behind the wall sits a screen capable of recording impacts. Now fire tiny particles toward the wall one at a time. Common sense says each particle should pass through one slit or the other and leave two concentrated bands on the screen behind. Two openings, two impact regions. Simple, but that is not what happens. Instead, the screen slowly fills with an interference pattern. Bright and dark bands spread across the surface in repeating waves. The exact pattern you expect if water passed through both slits simultaneously and overlapped with itself. The particle behaves like a wave, not metaphorically, literally. One particle fired at a time still builds a wave interference pattern over repeated trials, as if each individual particle somehow travels through both openings at once and interferes with itself before arriving at the screen. In a strictly mechanical universe, that outcome should be impossible. But then the experiment becomes even stranger. Scientists decided to place detectors near the slits to observe which opening the particle actually passed through. Nothing dramatic, just information gathering. The setup remained almost identical. Same particle, same wall, same screen. Yet the moment the path was measured, the interference pattern disappeared completely. The particle stopped behaving like a wave and started behaving like a localized object again. Two openings now produce two bands exactly as classical physics predicted. Observation changed the outcome. The particle did not merely reveal a hidden position that was already there. Its behavior itself changed depending on whether information about its path existed. Without observation, the system produced wave behavior. With observation, it produced particle behavior. The act of measurement separated two completely different realities. At first, many physicists assumed there had to be a mistake. Maybe hidden environmental effects corrupted the experiment. But over time, the results kept surviving every challenge. Different particles, different methods, different laboratories. The pattern remained. Matter behaves differently when its behavior becomes measurable. In ordinary life, observation feels passive. You look at the moon and nothing about the moon changes. You watch rainfall, and your attention does not alter gravity. Reality appears independent from observation, stable, external, continuous. But at quantum scales, the distinction between watching and interacting starts collapsing, because observing a particle is not like quietly staring at an object from far away. To detect something that small, you must physically interact with it somehow. You bounce light off it. You expose it to fields. You force an exchange of information. And at those scales, even the smallest interaction becomes significant enough to reshape the system itself. The double-slit experiment was not merely a new discovery. It dismantled the assumptions underneath classical thinking itself. The assumption that objects possess definite properties before measurement. The assumption that observation simply reveals reality rather than participating in physical outcomes. One by one, those assumptions began to fail. And once that happened, physics entered territory where intuition stopped working entirely. At this point, most people try to rescue their intuition. They assume the particle must secretly know what it is doing the entire time. Maybe the missing information simply exists beyond our current instruments. That explanation feels comforting because it preserves the idea that reality remains definite even when nobody measures it. Quantum mechanics refuses to cooperate with that comfort. Imagine firing particles one at a time again, separated by enough time that they cannot physically collide with one another. You would expect each particle to behave independently, yet the interference pattern still appears over time. Each impact lands as a single point on the screen, but together they gradually form the same wave structure. That means something extraordinary is happening before detection occurs. The particle behaves as if multiple possible paths coexist simultaneously. Not because scientists are confused about its location, but because the mathematics describing the system treats those possibilities as physically meaningful. Before measurement, the particle is not sitting neatly inside one definite state, waiting to be uncovered. Instead, its behavior spreads across several potential outcomes at once. This idea became known as superposition. In everyday life, objects occupy clear conditions. A door is open or closed. A coin lands heads or tails. Classical thinking depends on definiteness. But quantum systems evolve like overlapping waves of probability rather than fixed physical positions. Only when interaction forces a result does one outcome become observable. The particle does not travel through one slit while secretly hiding its true path from you. If that were the case, the interference pattern would vanish even without measurement. Instead, the mathematics works only if both possibilities remain active simultaneously until interaction destroys the overlap. The particle behaves as though reality itself refuses to commit in advance. This is where physics started colliding directly with language. If you call the particle a wave, it eventually arrives at the screen as a localized impact point. If you call it a particle, it produces interference patterns that require wave behavior. Every label becomes incomplete the moment you push it too far. Suppose you try determining which slit the particle passes through while disturbing it as little as possible. You attempt to preserve the interference pattern while still extracting information about the path. Something remarkable happens. The more information you gain about the particle's position, the more the wave pattern collapses. And the more the wave pattern survives, the less definite path information becomes. Reality seems to enforce a trade-off. Clarity in one property destroys clarity in another. This creates a fatal problem for classical certainty. The classical universe behaved like a completed story. Every object possessing exact properties, whether humans knew them or not. But the structure underneath quantum systems appears fundamentally probabilistic before measurement occurs. This is why so many physicists resisted quantum theory initially, even while the equations kept working with astonishing accuracy. It implied that nature itself operates differently from human expectation at the most fundamental level. Not chaotic, not randomly, but unresolved, as if reality contains competing possibilities evolving simultaneously beneath the surface, until interaction forces one outcome into existence while eliminating the others. Up to this point, the mystery seems centered around the particle itself. A particle behaves like a wave until somebody observes it, then the wave behavior disappears. Naturally, people begin imagining observation as something almost magical, as if human awareness somehow forces reality to change. That interpretation is popular, but it is deeply misleading. The real problem is not consciousness. The real problem is interaction. To observe anything in physics, information must physically travel from the system to the measuring device. That sounds obvious in ordinary life, but at quantum scales it becomes consequential because information cannot appear without disturbance. Observation is not passive. It is an event. Imagine trying to see a tiny dust particle floating in darkness. The only way you can detect it is by shining light onto it. Photons strike the particle and bounce into your eyes or instruments, but shrink that situation down to quantum scales. A photon capable of revealing an electron's position carries enough momentum to alter the electron's motion significantly. The act required to gain information physically changes the system you are trying to measure. You are not quietly uncovering reality from a safe distance. You are colliding with it. Suddenly, the double-slit experiment starts looking less like a mystical riddle and more like a structural limitation of nature. When detectors are placed near the slits, they interact with the particle through fields or photons capable of recording path information. That interaction destroys the delicate overlap between possible states that produce the interference pattern in the first place. The wave behavior collapses not because humans become aware of the result, but because the system itself becomes entangled with measurable information. Quantum mechanics is not saying human minds control reality. It is saying that extracting information from a system inevitably changes the system. That realization shattered the idea of a perfectly detached observer. Classical physics treated measurement like opening a window onto an already existing reality. Quantum mechanics replaced that picture Measurement became physical participation. Information and disturbance became inseparable. This trade-off became formalized in Heisenberg's uncertainty principle. The uncertainty is not merely caused by clumsy instruments. It emerges from the structure of quantum systems themselves. Position and momentum cannot both become perfectly definite simultaneously. Reality resists complete specification, and this reveals a profound truth. Suppose a detector records which path a particle takes, but no human ever checks the data. Does the interference pattern still disappear? Yes, because what matters is whether information about the system became physically available within the environment. Reality responds to interaction, not human attention. To observe is to interact. To interact is to disturb. There may be no viewpoint outside reality from which the universe can be examined without participation. The clean division between observer and observed dissolves. The universe is not a passive machine waiting to be inspected. It is a network of interacting systems where measurement is never separate from the reality it reveals. Just when physicists thought the framework of reality could not be further challenged, another phenomenon appeared that tested the concept of space itself. What happens when two particles interact closely and then move apart? Classically, the answer is simple. They behave independently. A coin flipped in one city does not instantly affect another coin on the opposite side of Earth. Objects stay where they are. Causes spread through space over time. When certain quantum particles interact, their states can become linked in a way that prevents them from being described independently afterward. Instead of behaving like two separate systems, they behave like parts of a single shared system, even after enormous distances separate them. This phenomenon became known as entanglement. Measure one entangled particle, and the correlated properties of the other particle become instantly determined as well, regardless of the physical distance between them. This implication deeply troubled many physicists, most notably Albert Einstein. Einstein believed reality should remain local and objective. Information should not travel faster than light. Physical systems should possess definite properties independent of distant events. He famously dismissed entanglement as spooky action at a distance. But nature did not care about intuition. Imagine two entangled particles created together and sent in opposite directions, one toward Earth, the other toward a detector far away. Before measurement, the system exists in overlapping possibilities. But once one particle is measured, the correlated outcome of the second becomes immediately constrained. Not eventually, immediately. If the particles already carried predetermined hidden instructions from the beginning, experiments should follow certain statistical limits. Physicists spent decades testing those limits. Quantum mechanics kept winning. The correlations exceeded what classical hidden variable explanations allowed. This does not mean messages are secretly traveling faster than light. Entanglement cannot be used to send controllable information instantaneously. But the mathematical structure describing the particles remains unified despite spatial separation. The relationship itself becomes fundamental. At macroscopic scales, the world feels divided into independent objects. Tables remain separate from walls. Human beings experience themselves as isolated observers. But quantum systems reveal that underneath those large-scale appearances, reality organizes itself relationally. Certain properties do not belong entirely to individual particles alone. They belong to the shared system connecting them. Instead of imagining reality as solid objects carrying self-contained attributes, physics started describing networks of correlations distributed across systems. The boundaries between this thing and that thing become less fundamental than the relationships linking them together. A universe where relationships are sometimes more fundamental than the objects participating in them. For most of human history, people imagine the universe as a giant clockwork machine. If an intelligence powerful enough could know the exact position and motion of every particle in existence, it could calculate the entire future of the universe with perfect accuracy. Tomorrow already existed mathematically inside today. Quantum mechanics destroyed that certainty. After decades of experiments, physicists reached a conclusion they never expected to accept. At the deepest measurable levels, physics does not predict exact outcomes. It predicts probabilities. Imagine a radioactive atom. Classical intuition says the atom must already know precisely when it will decay, but quantum mechanics says otherwise. The theory can predict the probability that decay will occur within a certain time frame with astonishing precision, yet it cannot predict the exact moment a specific atom will decay. The uncertainty is built into nature itself. Traditionally, probability had represented ignorance. If you roll dice, probabilities exist because you do not know every force and angle involved. But at microscopic scales, probability no longer looked like missing information. It started looking like the fundamental structure underlying physical events themselves. Physicists stopped asking, what exactly will happen, and started asking, what outcomes are most likely to happen? The equation Px equals \psi x, caret 2 became one of the most important ideas in physics. It does not tell you where a particle definitely is. It tells you the probability of finding it in a certain location when measurement occurs. And yet, the theory works with unprecedented accuracy. Modern computers, semiconductors, lasers, MRI machines, and entire technological civilizations depend on equations rooted in quantum probability. The predictions succeed constantly, but the conceptual picture underneath remains profoundly shifted. Possibility itself may be physically real before interaction resolves it. This does not mean anything can happen. Quantum systems follow strict mathematical laws. But the universe stops feeling like a machine built from certainty and starts feeling like a dynamic system where possibilities evolve continuously beneath observable events. At human scales, probabilities average out into stable patterns. Chairs remain solid. Planets follow predictable orbits. Cause and effect feel reliable. But underneath that macroscopic stability, the microscopic foundation remains probabilistic, not temporarily. Fundamentally, the universe is not irrational. It follows mathematical structures with extraordinary consistency. Yet those structures describe probabilities first and certainty second. Reality does not completely abandon order. It abandons absolute predictability. Physics discovered that the universe is not a perfectly determined machine moving inevitably toward a fixed future. It is something quieter, stranger, and far more fluid beneath the surface. A reality where certainty emerges only after possibilities collapse into outcomes. A universe where probability is not merely a limitation of human knowledge, but the very architecture of existence itself.